We'll get started here with Lecture 1. This is going to coincide essentially with Chapter 1 from the Hibbler text. I'm intending this to be for students taking statics class with us, but if you're joining us from somewhere else in the world, welcome. Hopefully you find these helpful. But again, I'm going to really focus on my students, but that's, again, happy to have guests. So we're talking about statics. This is going to be Lecture 1. I'll do these in 15-minute segments for a variety of reasons, but part of it is just keep this file size manageable, and also I think it just makes it a little bit easier to kind of go through them if you break it up into chunks, I find, and I think I've heard other students tell me this. So what are we doing here? This is statics. That's our fundamental subject we're looking at here. It's a fundamental engineering course. It is very simply the study of objects that are static or at equilibrium. As you can tell, my writing is not all that good. These do not accelerate, is what we're saying here. We're talking about objects that do not accelerate. The good news is I don't write words very often, so you're not going to have to decipher my chicken scratch very often. A lot of what we're going to do is going to be math and calculations and things like that. So as you're watching these videos, you need to be taking notes. Simply put, take notes as you're watching these videos. If you're just watching me and listening to me, maybe that's helpful for you, but I think for most people, that's going to be boring and it's not going to be as engaging. Take notes. And I'm kind of stalling a little bit here. If you don't already have a notebook out with pen, I'm giving you a chance to do so. Sorry, I don't clear my throat a lot. Hopefully it's not too big a deal. Things that do not accelerate. Typically in a statics course, we are also looking at things that do not deform. So in a dynamics course, we start looking at acceleration and change motion, things that are not at equilibrium. In a strength of materials or mechanics of materials course, we'll start looking at objects as they deform. How do they deform? When do they fail? What do the failures look like? But it all starts with being able to analyze an object that's in equilibrium and determine what forces are required to keep said object static or at equilibrium. It is a subfield of mechanical physics. And it's a subfield of mechanics. Physics, the mechanics portion of a physics course. Often, physics courses are often broken into two pieces. You've got kind of your classical mechanical physics, Physics 1, and then you've got your kind of your more thermal, optical, and electrical, magnetic Physics 2 courses. Often how those get broken out. I'm expecting that you have had a calculus-based Physics 1, and I'm expecting that you can do both derivatives and integrals in one variable, meaning you have good working knowledge of algebra and trig. If that's not you, you will really struggle in a statics course. Make sure you've got those in place. All right, so I'm going to slide up here. Let's talk briefly. So again, I'm kind of following along in the Hibbler 14th edition statics text. In chapter 1, and I agree with what he's doing there, so I'm going to do the same thing. He kind of reintroduces Newton's 3 laws. He talks briefly about Newton's law of gravitation as well, but he talks about Newton's 3 laws, and we're really going to focus throughout this course on Newton's first law. And that is simply saying that if I add up all the forces acting on an object, and I find those forces are equal to 0, that means that the object is not accelerating. Acceleration is 0. This is static, or this is the study of statics. Newton's second law Now I am simplifying here. If you go back and look at the original translation of Newton's first law and second law, this isn't exactly the way he presented it, and that's okay. This is how classic physics is kind of interpreted over the years, and this is how we often would teach students. The second law essentially says that if there is a net force, that net force will cause an acceleration that is proportional to the mass, so long as the mass is constant. Really what it's doing is it's actually causing a change to the momentum of a particle or a set of particles. If we look in a fluid mechanics course, we have to treat it as a change in momentum. But this is really, in a Physics 1 course, this is what we're looking at. And this is really going to be kind of our focus in those of you that go on to take a course called Dynamics. Dynamics is very much the study of motion. You're going to look at Newton's second law, both in a linear translation and also in terms of rotation. We won't deal with Newton's second law here much in the statics course. Almost everything's going to revolve around Newton's first law. We will see, though, on a regular basis, Newton's third law. Newton's third law. Who can tell me what Newton here? If I were in a classroom, here's what I would ask: who can tell me what Newton's third law is? And I would wait, and we'd struggle, and we'd kind of kick it around a bit until somebody comes up with the idea that for every action there is an equal and opposite reaction. We will definitely see action-reaction quite a bit throughout the semester. So that is, you'll see this applied in both statics and dynamics. We'll apply Newton's third law. There is Newton's law of gravitation, which essentially says that the force of gravity is proportional to a gravitational constant, capital G, the product of two masses, and the square of the distance separating the two. Now this translates down into where we say that weight is equal to mass times little g, where basically we're saying if little g is equal to capital G times the mass of the Earth divided by the radius of the Earth squared, we essentially get the gravitational constant. And so if m1 is u and m2 is the Earth, and you've got the distance of the radius of the Earth separating you from the center of the Earth, and you've got your universal gravitational constant, the product of those quantities becomes the gravitational constant. And that's true. It doesn't matter what planet you're on. Here I'm subscripting an E for Earth, but the same would be true on Mars, on Pandora, whatever planet you happen to be on. We're going to call this 2 of, if we're doing this hardcore, I'd go ahead and put my name, and it's still Lecture 1 Statics, and this is going to be page 2 of whatever we end up being. Right now I'm just going to keep track of page 2 of 2, but let's just say L1, right? So I know it's still at Lecture 1. I don't get my notes mixed up after a while. Okay. Now, if we continue on talking, basically in Chapter 1 of most statics texts, ours included, is really going to give you an introduction to a lot of stuff that you should have seen already. I am hoping that you have seen or talked about in a course before units and dimensions, which are not the same thing. Right? Units are not dimensions. Units measure dimensions. Units are standard quantities we use to measure particular dimensions. So if we say, well, what are some examples of some dimensions, right? Well, that would be the common ones we'll deal with in this course will be things like length. And fair warning, I tend to write my L's this way. It's kind of a cursive L, and I just don't always, for a lowercase l, I don't always translate it to a block letter. Time, mass, and I tend to capitalize force out of habit. It's a good habit to be in, I can tell you from experience. This is a design, I'm teaching this for engineers in the United States, meaning we have to use what we often call the English units. The rest of the world calls it the imperial units, or some places will call it the American customary units, because Americans are about the only people in the world today that use them. But if I'm training engineers to function in the United States, I still need to train you in what we call often English units. I say that. I actually said this to a group of students not too long ago, and they're like, yeah, I've never heard them called English units. I always heard them called imperial. Okay, that's fine. English imperial, American customary, we're referring to the same thing. The standard units we'll typically see in this course in the English set would be feet and inches. There are 12 inches in a foot. Occasionally you will see yards. There are 3 feet in a yard. On rare occasion we may encounter miles, but I don't think that's going to occur very often in this course. Miles, 5,280 feet in a mile. In metric, of course, it's just the meter. You will probably encounter centimeters, on rare occasion maybe kilometers, but just about everything we're going to deal with would be something you can pretty well put on a piece of paper. Feet, inches, and meters are going to be the most common thing we'll use, maybe the occasional centimeters. Time, it is the unit of seconds in both systems. In the unit of mass, right? So if dimension is mass, the unit in the metric is often the kilogram. Right? Fair warning, I will write my kilograms. I tend to write my units in cursive, and I tend to write them very fast and sloppy. Fair warning. Right? In the English units, often in this course we will deal with slugs. It's very common in a mechanical textbook. You'll deal with slugs. If you're taking a thermodynamics or a fluid mechanics course, you might deal with the pound mass, the lbm. Typically in the thermal science course, we might use pound mass. We're going to talk about what that is in just a second. If I write that in cursive, it's going to look like this. LB with a subscript of M. Again, I will write my units quickly. You'll get used to it. I will often write them in cursive. Just fair warning. Unit of force. Again, LB for pound is the English unit, and when I write it, I'll write it in cursive. If you're dealing in a course like a thermo course or something like that, where you have pound mass as an option, if there's no subscript on anytime there's no subscript on the LB, you should assume that it's force. If it's specifically mass, you need to subscript it with an M. And again, in a statics course, it's pretty rare we deal with pound mass. We're going to talk about it today, and you may not see it again the rest of the semester, and that's okay. There is occasionally you'll encounter a unit, the kip. 1 kip is a kilopound, essentially. That's 1,000 pounds. In the metric system, it's the Newton. Good old Newton. The weight of an average apple, is about 1 Newton. Okay. The important bit about units is conversions, of course. All conversion factors equal 1. And here's where I would ask, okay, what happens when you multiply a number by 1? And of course the answer is, well, you get 1, right? You get the answer back. You get the number back. The number doesn't change. Well, yeah, when you multiply by 1, you should get the same number back. Right? Okay, so the idea of conversion factors, I multiply by some quantity that equals 1, some ratio that I have the same value in the top and bottom, the same amount, or the same units top and bottom, and so I end up with 1. What that means is if I've got 1 Newton, that is 1 kilogram. That's the amount of force required to accelerate 1 kilogram at a rate of 1 meter per second squared. So what that tells me is my conversion factor, 1, if I solve here, basically I'm going to move everything over here with the Newton. That is 1 Newton per kilogram meter per second squared. And how I would normally write that is I would say, well, that's 1 Newton second squared per kilogram meter. All right, I'm going to pause here. That's a good 15 minutes. I'm going to pick up on the next video from there.